Good afternoon, everyone, and welcome to the fifth and last webinar of the spring session of the EMOS 2021 webinars. My name is Caterina Giusti. I'm Professor of Statistics at the University of Pisa in Italy, where this session is hosted. And today, I will also act as the webinar facilitator. Now, let me first explain for any newcomers that EMOS stands for the European Master in Official Statistics, a joint project of universities and data producers in the EU member states, FTA, and EU candidate countries. If your university is interested in applying for the EMOS label, please consider that the permanently open call for universities is available on the EMOS dedicated page on the Eurostat website. For staying in contact with the EMOS news and community, please follow the EMOS Twitter. The EMOS Twitter account is @EU_EMOS. It's now time to start with our webinar. Before I give the floor to our speakers, let me first briefly explain how we run the webinar today. This here, the EMOS webinar stream on the EMOS YouTube channel, where you can already find the recordings of the past webinars. As a participant, you can watch and listen to the webinar. To use the chat to interact with the presenters, you need to log in YouTube using a Google account. We encourage you to prepare your question and pose them to the presenters during the presentation or the question breaks or the final discussion. Should you have any technical problem or question, you can use the email address that we already indicated in the chat. We are now ready to start. Today, I have the great pleasure to host two speakers, Piet Das and Marco Poets. Piet Das is a senior methodologist and statistician in Netherlands, where he leads the research on big data. He is a professor by special appointment on big data and official statistics at the Eindhoven University of Technology, where his work focuses on the development of big data methodology. Piet teaches big data online at the University of Utrecht, University of Maryland, and the University of Mannheim. Marco Poets is a methodologist at Statistics Netherlands. He studied cognitive science, which is a combination of cognitive psychology and artificial intelligence, and received his PhD in psychophysics. At Statistics Netherlands, he works on big data and data science. So today, Piet and Marco will present about machine learning from a statistical perspective. So Marco, the floor now is yours for the first part of the webinar.
Thank you very much, Caterina, and thank you for the invitation. So the title is Machine Learning from a Statistical Perspective, and actually the idea of a subject like this started a couple of years ago when my manager came to me and said, Marco, what are we going to do with machine learning as a methodology? And I told her, well, don't worry, we don't need to use machine learning as a methodology for official statistics. And I'm still convinced about this. This is a bold statement at the moment that you're going to give a presentation on machine learning from a statistical perspective. But the reason why I said it to my manager at that time is still valid. Machine learning is a field which has a broad scala of methodologies which are used for machine learning, but many of them are still not really usable for official statistics. And during this presentation, I will explain why. I will show you some caveats in using machine learning from a statistical perspective. And I hope that it will help in making sure that machine learning techniques will slowly evolve into statistical methods so that we can use them very well for official statistics. Okay, so let's start. This is the setup of the presentation. We will start with a short introduction in artificial intelligence and machine learning. It's really short because I don't have hours to talk about it. Then I will go to one of the first subjects, bias and classifications. Then I will look at the asymptotical behavior towards annotated data. Sounds really promising, but I don't know if it's that big as the title suggests. Then I will switch to Piet. Piet will say something about correlation versus causation, representativity of training sets, and concept drift. And finally, the floor is mine again, and I will finish with explainable AI. So first, what is artificial intelligence and what is machine learning? So artificial intelligence was coined in the 50s. It was the birth of artificial intelligence. And I won't go into many details, only that the hopes were really high that that people thought that they could actually simulate a human being on a computer. That is actually called hard AI, which is mentioned here in the list. Luckily enough, we also have soft AI, and these fields are actually much more close than the hard AI part. Hard AI is actually much more about philosophy. So they started really promising, and artificial intelligence had actually sort of nervous breakdowns a couple of times because they promised a lot and they couldn't get to reach the goals that they had. And but still, it's a very interesting subject, and it's also very helpful. Okay, one of the terms you will actually find in a lot of literature is symbolic versus sub-symbolic, and this all has to do about how representations, because artificial intelligence runs on representations, how they are formed. In the symbolic part, we are actually looking at symbols. We are actually looking at objects and concepts, and we are modeling the relationships between them. In the sub-symbolic approach, we are actually using much more fluffy representations, and you can actually see them back in neural networks and, of course, deep neural networks. Everything runs on the representations, like I already stated. And actually, AI is much about searching and optimizing in these representations and solving problems in these representations. And another subject which is interesting is machine learning. And that's actually the reason why we are here. We are talking about machine learning. But you cannot see artificial intelligence and machine learning apart from each other. They are actually forming one field. When you look at machine learning itself, there are also some terms you need to know. Machine learning is about learning strategies for computers. And you can see there that there are differences between supervised and unsupervised learning methods. And something that is unsupervised, this means that you don't need any annotated training material, is clustering. You just let the machine decide on what clusters it has to find. But also PCA. A PCA is something like an unsupervised learning method. And PCAs are really good known by statisticians. Other supervised techniques are classifications and regressions. Now, statisticians, I don't have to tell them anything about regressions. Also, classifications are quite well known. Actually, I will build my presentation around one that you all know quite well. Actually, I will focus this presentation a lot around classifications. So what are classifications then? A classification is actually a method where you have a lot of features of objects, of cases, and you use these features to find out to which class that object actually belongs. That's actually what you do with classification. The one I will focus on, which is well known by statisticians, is logistic regression. But you can also use decision trees, which are really clear on what they are doing because of the fact that you can see all the decisions, support vector machines, and neural networks. And of course, there are much more of these different methods. Logistic regression. What I like about logistic regression is that you can explain what it is to machine learners. You can explain something to machine learners and to statisticians at the same time. Once I had a discussion with a machine learner and a statistician, and they both asked a different question to me. One asked a question, what is a neural network? And the other one, what is logistic regression? And I could actually give the same answer. Why? This is just, for someone working in machine learning, this is just one node of a neural network. So you have some inputs, you have a summing mechanism, and you have a nonlinearity for generating the output. For a statistician, this is a logistic regression model, which is stated here. It's a weighted sum of a feature vector. We add with a bias, or like statisticians call it an offset, and I put a logistic function on top of it as a nonlinear function, and I get something out of here, and that's a p-value. And actually, when you fulfill all the requirements of a logistic regression, this p-value is actually the probability that an object with the features that I have here. What is probability that it is, for instance, a positive or a negative item? So it's a good thing to do. One of the things I would like to explain is the confusion matrix. And I would suggest that all of you who don't know that much about confusion matrices, just go to Wikipedia, the Wikipedia page on confusion matrices, because it's an excellent source for explaining the confusion matrix and all the measures you have on the confusion matrix. I just took the image from Wikipedia over here because it's so explainable. I could try to do it myself, but it's so good that you should actually just have a look at this one. So what is a confusion matrix? You look at what the true condition was of an item. You look what the predicted condition is of an item, and you see if you made any mistakes. And for that, you can divide it in 4 categories. The correct categories, the true positives, where the condition positive and the predicted condition positives are the same. So the model predicts what the model actually should predict. The true negative, also the model predicts what it should predict, but then for the negative cases. And then 2 error situations. For statisticians, it's much easier to talk about type 1 and type 2 errors. For machine learners, it's much easier to talk about false positives and false negatives. And that's what I like about it. It's covering both worlds. So then when you have this confusion matrix, you can define some measures on them. And 2 of the most important ones are the precision and recall. You see them here and here. We start with the recall. The recall is the number of true positives divided by the number of positive items in the data set. Whereas the precision is the number of true positives divided by the number of positive answers given by the algorithm. And precision and recall are used very often, and there is another one which is just some average of precision and recall. So it's not. But if you want to know more about it, just visit this page. So what we want to do with all this information is find out how good a classifier actually functions. So I have the classifier with the inputs and a certain output. And when I just pick up the signal over here, I can just say that the scores which come out of here, I plot them at the x-axis, and the red curve is then the distribution of all the negative cases, and the green one is the distribution of the positive cases. And that's actually where we are calculating with most of these classification algorithms. So we have here the negatives and the positives in the distribution, and now we have to make a decision. And how do we make the decision? We put a threshold somewhere, and we can put it actually just in the middle at the 50%. And at the moment, and that's what you know when you did psychophysics, because this comes from signal detection theory. At the moment, that's the distributions have the same variance for the negatives as the positives. And they are both 50-50 represented. Then the threshold is exactly here at this spot. It's the best threshold you can actually get, and you can actually prove it that that's the right point. But sometimes you just want the threshold somewhere else. For instance, oh, I'm sorry. We can now calculate the true negatives and the true positives just by looking at this threshold, and integrate under the curve from that threshold to infinity for the true positives, and from minus infinity to the threshold for the true negatives. Then the false negatives are just 1 minus the true positives, and the false positives are 1 minus the true negatives for the rates. Okay. So now I come back to the point where I actually was talking already. So at the moment that I put the threshold much higher, so I can choose where I put the threshold. When I put it much higher, then I will have high precision and a low recall. And sometimes you want that. In certain cases, You just want to be very careful in detecting and saying that something is positive. And in other cases, you just want the opposite around. So you have a low precision and a high recall. And that is at the moment that you don't like the false negatives that much, and you actually want them, most of them, in there, high recall. And there are situations that you want that too. For instance, in detecting cancer in X-ray images, then you actually want that threshold very low. So it's from a machine learning perspective, it's easy to understand why you sometimes want to put the threshold quite low, and sometimes you want to put it quite high. From a statistical point of view, you want the threshold at a certain point. I will come back to that later, but first I'm going to tell you something about another measure you can actually put on a classifier, because now you saw that the performance of my classifier is dependent on the threshold. And signal detection theory, which comes from electronics and from psychophysics, actually came up with an idea to overcome that problem. And I like this measure much more than all the other measures, because it just integrates out the threshold. So what do? They define the receiver operating characteristic. So they calculate the false positive rate and the true positive rate. And they plot the false positive rate against the true positive rate. And it just means that you vary this threshold for each and every measurement point. Then you get this curve. When the curve is equal to the orange line, your model is not able to discriminate between positives and negatives. At the moment that it is much higher, for instance, it's going up here and to the right here, then it is perfectly able to discriminate between positives and negatives. And in this case, it's somewhere in between. A measure on this is the area under the curve, where you actually calculate the area, this area, which I'm showing here. And it is actually a measure which is independent of the threshold. So it says something like, independent of the threshold that you use, you should optimize your threshold. But this model is actually very good in discriminating, or is very bad in discriminating. Then I come to bias in classification, because bias is one of the biggest problems in official statistics. When you are making official statistics, you don't want to have a bias in your result. So we are always looking for unbiased estimates. And if you want to make an unbiased estimate, all the steps in your process should be unbiased too. Otherwise, you will not be able to get an unbiased estimate. And to give you a feeling how easy it is to have a very good model, which is really really biased, I will show you this one. And we are going to train, all of us together, a model which has 99 red marbles and 1 green marble. And I counted them, there are 99 red and 1 green. So, and the question now is, which model can predict the color correctly in 99% of the cases? Remember, I have 1 green and 99 red marbles. And there is actually a very simple model which can predict and correct in 99% of the cases. And it is a model which always predicts that the marble is red. Actually, this model has a very high recall and a very high precision. The precision is 0.99, I think, and the recall is 1. But actually, when I'm going to change the proportions of green and red marbles, for instance, I'm going to change the number of green marbles to 50% of the number of marbles, then actually the model is really not working well anymore. So at the moment that you train a model with a certain percentage of positive items in there, you should be really careful what it does at the moment that you don't have that proportion anymore. And I will show at the end of this block on bias in classifications how dramatically this can go wrong. But first, a method by Quentin Mertens, who got his PhD degree, I think 1 or 2 weeks ago, on this subject, misclassification bias in statistical learning. And he proposes a method where you look at the confusion matrix and go and see what you should do with confusion matrix to make sure that the estimate actually gets unbiased. So at the moment that an estimator is unbiased, at the moment that the quantification of the number of items that are positive is unbiased, because that is what we are interested in making official statistics, then at that moment the true positives and plus the false negatives should be equal to the true positives plus the false positives. And the other way around, the true negatives plus the false positives should be equal to the true negatives plus the false negatives, because the predicted condition negative should be equal to the condition negative, and the condition positive should be equal to the predicted condition positive. This is only the case at the moment that the false negatives are equal to the false positives. So that's and you can find a method to actually find this the threshold, adjust the threshold in such a way that this is the case. Another approach that we worked on is an approach where we look at the distribution of scores which comes out of the model. So suppose I have a new situation, I have a trained model, and I'm going to apply it. I trained it in 2008, and I'm going to apply it on 2010 data. Then I will see, for instance, a distribution like this when I don't have any concept drift, like Pete will explain later. And what I can do then is take these scores and actually look at how they are built up in the distribution of negative items and positive items. And I can use a maximum likelihood estimate to actually estimate the A's here, where A is a proportion positives in the population. This is actually a method which works well. We used it already in practice in some situations, and it seems that this is really a way to go. Here is the dramatic effect that I wanted to show you. So I have here the simulated data set. I simulated one data set with 25% positives, one with 50% positives, and one with 75% positives. And I looked at the outcome on a test set varying from 10% positives to 90% positives. And here you see the results for the three different models when I do that. And you actually see that the model is actually good in predicting the true proportion positives at the moment that they are very close to the real trained proportion positives. When you adjust, when you try to estimate the proportion positives using the maximum likelihood method that I presented, you see that they are actually completely the same. We also did it for this little paper that we are going to present on a conference next month. When you are going to do this on the banknote data set and you corrupt it by leaving out some of the features, then you see that that again there is a strong bias towards the proportion positives in the trained data set. And with the machine learning method, with the maximum likelihood method, you actually correct it quite well. So you can correct for this kind of bias. Then the asymptotical behavior towards annotated data. As already introduced, as I was already introduced, I'm a psychophysicist, and I worked on visual science. And at the moment that I heard that people are actually using a human annotated data to figure out if something is a positive or a negative item, or what class an item should be, I started to get worried. And the reason why I got worried is actually depicted here in this slide. Human beings are really not that good in having an objective judgment of what the ground truth is, whatever the ground truth is. So, for instance, here, these two tables are exactly the same. But every person who is joining this webinar will say that this one is a different form than this one. The only thing that happened is that this table was rotated, nothing else. So we are really not very well able to see that. These persons are not seen as equal-sized, whereas they are actually equal-sized. Then you have these kinds of images where people switch in their observations. And if you look up the color constancy and the dress, you will see this image, which actually shows that even our color perception is very much biased towards other things than the real color of the object. So that's actually why I'm worried. To what extent is the observed ground truth the real one? Machine learners always say that their training set is the ground truth, but is that really true? Is that that thing that people are observing, if it is on aerial images of roofs for detecting solar panels, or these are messages of people saying that they have some symptoms of COVID, or these are websites which are scraped and we are looking at artificial intelligence company, it's all the same. The question is, to what extent is the observed ground truth real? And that's why I don't like the term ground truth like it is used at this moment. And I'm looking with Lianne Ippel at this moment about the implications of that, of a good definition of ground truth and the definition that we are using now for ground truth. So, and then I come to my asymptotical behavior, because when you look at it, then you see that you are actually training your models with human annotated data at the moment that you are using human generated data sets. And the model will never be able to outperform that human behavior. So when you want to have a good classification, the question is if that is really good. And I'm actually suggesting not to use any human annotated data anymore. No, I'm suggesting that we should put effort in doing research and how humans observe the images that they are actually classifying or the text that they are classifying. And because this is really worrying, especially for an official statistician, especially because you can never figure out what mistakes are present in the model or in the data set, because the wrongly annotated data is in the training set, it's in the test set, and it's in the validation set. How can we detect these errors? So I put this image here because it's an impossible triangle. We all see a triangle and we get all the feeling, even though we know it is impossible, we all get the feeling that it is possible. And we actually see that it is not possible, that this triangle is impossible at the moment that we have it as a 3D object and we start to walk around and we see that actually here the triangling is breaking up in two parts. So it's yeah. For me, ground truth is really something we should work on. Okay, and now I switch to Piet because Piet is now going to continue with the rest of the
we can. We have time, I think, for some quick questions. We actually already received one for you, Marco. So I'd like to know a bit more about the maximal likelihood correction method and how and where it is already used in production, if possible.
I think Piet can also give an answer about how far it is from production, because he is using it in some of his work. We have a paper on it. I can actually, after the presentation, I can put the link to the archive version of the paper. I can put it on YouTube. So then you can actually read the piece. It will actually be presented at the, and now I hope I say correctly, the Symposium on Statistics and Data Science, which is next month. Yeah, it's the other way around. Yeah, okay, it is statistics and
that's science and statistics.
Yeah. So that's where you can see it. Okay, thank you.
Yeah. I don't see any other question for the moment, so I think we can go on with Pete. In any case, we will have another question break and then the final discussion. So I suggest to go on.
Yeah. I have to share my screen, which is a challenge. Hop. Okay. So this is a section about correlation and causation. As Marco told you about, that there are a lot of things you can throw into a machine learning model, and if you use lots and lots of data, then the model that the machine learning algorithm eventually produce will be very there will be a lot of variables in there, and in that case interpretation is quite challenging, because you have lots and lots of variables, and it's clear that the variables included are correlated to your target variable, because that's what the model is training on. But the interpretation is difficult. Correlation does not imply causation, and causation, looking at what variable causes or affects the target variable, is very important in this case. And I'll start with a very simple example to illustrate you what causality is all about, and that's the obvious example of the ice cream sales and the crimes, which is purely a data set, but it contains data on ice cream sales and crimes, and they both are going up in the data set. So over time, you see an increase in ice cream sales and an increase in crimes. That's because they are associated, but there's no causal effect, and the factor that's causing it, the variable that's causing it, is the confounded temperature. Because the temperature goes up in the data set that you have, you see an increase in ice cream sales and an increase in crimes. And the problem with machine learning is that it can pick up the variable ice cream sales and the variable crimes and include it into the model, but in fact it should pick up the variable temperature. It should pick up the causal variable there. And this is a very interesting topic at the moment, and a lot of work is done in this area, and it can also reduce, certainly reduce the number of variables in the dataset if you're able to do that. So it's more important in the machine learning world to look at, to study causality between the variables, and you want to know which variables have a correlation to the target variable. And the challenge can be attacked in different ways, and I'm not going to explain everything how causal studies work. But you see a lot of people looking at seasonal effects. The example I gave you is there's a seasonal effect, and you know there might be a confounding variable related to that. If you're able to do an experiment, you can see how the variables you're interested in are related to one another. They call that a treatment effect. You can do an experiment with and without a particular treatment and keep the rest as the same as possible. You can try to intervene if you're able to do that, to see what happens if I intervene and if I prevent something from happening. What will a study then? And you can also look at, okay, you have a particular situation going on in your data set, but what would have happened if I didn't have that situation? So you're looking at counterfactuals. There's a lot of different approaches for looking at causal studies. And one of the reasons why domain knowledge is always so important is because it contains a lot of these causal relations are in the head of the people with that domain knowledge. Particularly if you look at big data or given data, then causal studies are especially challenging because you can't intervene then. You have to look at the data and it is what it is. And you have to try to find that causal relations in such a data set. It's an extremely interesting topic, and a lot of work is going on in this area. If you want to know more about it, look at the paper of Pearl on causal inference. It gives you an overview. And I've recently discovered a paper of Schulkopf et al., and they look at causal representation learning. So they try to include those causal relations already in the model, which would be great, because I would love to have know more about such an approach. The other topic Marco mentioned is about representativity of training sets. It's very important to train your machine learning algorithm on something that's representative of your target population. But what is representativity exactly? Everybody who knows a lot about sampling theory knows that if you take a random sample of your population, that's really a very good way to obtain a representative sample. But if particular groups in your population don't occur that much, and you're very interested in those groups, you can call it a small area. Then it's a good idea to oversample your representatives of the small area more in your training set, so you can use stratification there. And in the machine learning area, that's valid as well. So you can look at clustering of features and try to overrepresent particular groups in your training set, or you can look at background characteristics and try to affect those for including them in the data set. And to give you an illustration of how important that is, let's look at representativity in general. I'm from the Netherlands, so usually if I publish the statistics on people, then I look at the Dutch population, and this sphere represents the Dutch population. If I take a big data source, and let's take the most difficult one there is, let's look at the Dutch social media, then everybody knows that not everybody in the Netherlands is active on social media. There's only a particular subpopulation active on social media. So that's the data set you have to deal with, and somehow you try to infer from that population, try to say something about the total population in the Netherlands, your target population. But you have to be aware that if you look at social media, that usually the data set you have is a particular set of messages containing a particular set of words, and that's also a subset of your Dutch social media subpopulation set. So you have a particular set of messages created by a particular group of people, and somehow you're trying to make that use that data to infer that for the total population. So you have to a subset of a subpopulation in a whole population. And most likely what you can use the data set that you have collected for is try to infer something about similar people that are also active in social media. But the challenge is try to expand those conclusions from that particular subset of Dutch social media population users to the whole population users. And that's something you have to keep in mind, because the most difficult part here is how can you infer something from the Dutch population that's not active in social media based on data in social media. That makes it a very extreme difficult one. And this is something you have to keep in mind, is that the data set I'm using, the training and test set and the validation set, how well does it represent the target population I have in mind, and how can I make the best decision on that? And for me, what usually works well is just illustrated with something that we run into a practice, because we try a lot as statistical analysts and we make lots of mistakes, and we learn a lot from those mistakes. Let's give you an example. We did a study on the detection of platform economy companies in the Netherlands, and usually this research starts with a question from somebody in our office, and they contact me and they say, Pete, is it possible to detect the platform economy companies based on the text on their website? And in essence, they ask one question, but they also mean something else. And here representative is a key issue, because the first question is it possible to develop a model, a machine learning model, that can, based on the text on the websites, determine if something is a platform economy website or not? That's doable. That's not a problem. But developing a model and then applying that model to detect all the platform economy websites in the Netherlands is a different question. And Marco told you, gave you already a lot about the clues about how difficult it is. And for people that find it difficult to think about what a platform economy website is, in principle, the obvious examples of this are Amazon, Airbnb, and Uber. So a website where people visit and order stuff. You can call it a representative of the digital economy, but I'll call it a platform economy website. Now, develop a model is possible, and what usually happens is then they give you a list. Pete, these are examples of websites of platform economy companies identified by our experts. And in my case, they gave me a list of 600 positive cases. Wow, great. But I can't build a model based on positive cases alone, so I have to get a set of negative cases as well, because I want to build a classifier that's able to discern between both. And what we usually do is draw a random sample from the companies in our business register, look for the company websites, manually check if there is not a platform economy website in there, and then equal the number of positives and negative cases, scrape those websites, and you can make lots and lots of decision about it and process the text in lots of different ways. But in the end, you have 1,200 cases, and it's supervised learning, so they're classified as positive and negative. And you try lots of models and different approaches. Our final conclusion was that a supported vector machine with a linear kernel works best. It's possible to separate the positive and negative cases by 82% of accuracy, which is already a good start for a first trial. And then you looked at the model, then you look at what are the words that have the highest weights assigned to them, and those words are register, of company, login, platform, sign up, and that gives you a clue about the fact that it seems to suggest something that's indeed related to having a platform economy. And as Marco already shown you, such a model can not only indicate if a website, in this case text, is positive or negative, but it can also give you a probability of being positive or a probability of being a platform economy website. And if you make a histogram of those probabilities in your test set, then it's great if you see sort of a U-shape emerging, which means a clear separation of the negative and the positive cases. And that was the case here. And we subsequently applied this model. So we said, okay, we developed a model on 50%. It seems to work. Well, there are indications that it detects a platform economy website. Let's throw it on to a large data set we have of all the websites that we could assign to the companies in our business register. And this is the result. It's a plot. And there's a huge bump close to zero. So a lot of those websites are clearly not platform economy websites. But after 0.5, which usually is a decision boundary where the number of positive cases should be higher, you can see that the histogram is still going down. And only if you look into the right, close to the value of 1, and I'm zooming in here, then you can see that there's a small peak which suggests that this could be a group of platform economy websites. This is a small area problem again. You developed a model that clearly shows that if you have 50% positive companies and 50% negative, that it's possible to separate them, and fairly well. But in the real world, platform economy websites are only a small number of websites. Suppose in the 600,000 websites, you would only have 100 websites indicated, or 600. The 600 websites we trained it on as a positive case, that's clearly a very low percentage. So there are lots and lots of false positives in here. And this is one of the reasons, this is one of the examples in which we applied the model that Marco discussed about, and it works really well. It seriously reduces the number of false positive cases. It doesn't remove them all, but it really helps in identifying them. And the most interesting thing of this study is the fact that we actually draw a sample from those highly scoring companies, and we send them a letter, a survey, in which we ask them questions about if they are a platform economy website or not. And that confirmed that this model is indeed able to indicate if a website is a platform economy website or not. So that's a nice example. Solutions to deal with that: you can really develop a model on 50% positive and negative cases just to demonstrate that it's possible that those two are different, and get an indication of what's important or not. But if they are really a minority group, then you have to do additional corrections here. You can apply a correction method, the one suggested by Marco earlier, by making sure that the number of false positive, false negatives are the same. You can also try to train the model on a more realistic ratio. You can, for instance, say, okay, let's take 20% positive cases and 80% negative, and see if that model is able to pick it up. You have to take a different metric to do that. Balanced accuracy would be great. In that case, your average accuracy is a result of the negative cases classified correctly and the positive cases classified correctly. Or you apply a combination of both. And at the moment, we're looking at what the best approach is. And I guess we will come on with a hybrid approach here. And you do a lot of manual checking and classification. Really interesting and important topic. Then the third topic I'm going to talk to you about is concept drift. That's a real challenge for machine learning algorithms and for statisticians in general. And this is an example where statisticians can actually learn from machine learners. Because if you develop a classification model, for instance, the one I talked about, then you assume that at a particular point in time you build a model, and then you more or less assume I'm going to use a model again and again over time, and I'm going to use it every year to create a statistic. But that assumes that the relation between the data you used in your training and test set and the model is stable. That's not always the case. That relation may drift over time. That's what time series experts call non-stationary. And for text-based models, that's obvious. If I build a model to detect innovative companies, that's a topic I talk a lot about. It's clear that at this point in time, innovative companies use particular words, but you can easily imagine that over 5 years, the words they use are slightly different, and your model has to be adjusted for that. That's what's called concept drift. And if you see a change resulting in the output of your model, you can ask the question, is this a real effect, or is it caused by concept drift? And how I'm going to deal with that, and how I'm going to discern between those two. And I'm going to give you an actual example of what I worked on. That's for the detection of innovative companies. So we have a survey that detects that is sent to companies, and the answers they give to that survey is used to indicate which companies are innovative or not. That's the input for a training model. We looked at the text on the website of those companies, and we were able to build a model that worked really great. The model had an accuracy of around 90%, and there are clear differences between the words they use. But when we applied that model over a longer period of time, something strange occurred, and we scraped a similar set of websites during that time. We applied the model on that. And we saw that it is degrading. The number of positive cases decreased over time. It's often known as model degradation, but in fact, it's an example of concept drift. As this is the plot I'm showing you there. At TS0, the 0 month the model was developed, it was even a bit higher than 90%. After 3 months, everything worked well. Those websites scraped after 3 months, and we applied the same model over that. But if you looked at that after half a year and a year, it's clear that the accuracy of the model decreased over time. In the end, it was close to 65%, which is it's very close to the 50% of random assignment. So that's not a good thing. So what's going on here? We were a bit surprised. So we talked to statisticians. What's going on here? What do you think is going on here? And how should we deal with that? And I also talked with machine learners. And both gave different reactions. And it's clear that if you're dealing with concept drift, the concept drifts over time, and you need to correct for that. That's caused by the fact that websites content changes over time. That's obvious. If you use the web as input, as data set, it's constantly changing. Websites go on and off, but also the content on the website changes, and this obviously affects the outcome of the model, and that we held this model constant here. Traditionally, how to deal with that? Statisticians suggest, you should just retrain your model in the new data. Just use the old classification you have, extract the new data, retrain your model. This doesn't work because in principle you get the same results that I've shown you already. A newly trained model on a new data set doesn't work that well. What do machine learners say? We are used dealing with that. Just keep your data set that you have, your training and test set, but add new cases, new classified cases to your model, and retrain the model on the combined set. And this is an approach they commonly apply when they have to deal with data streams. So they measure a particular concept in a data stream. The model works really well, and they see a small drift in the result of the model, and they look at new cases, classify them, and add them, and retrain the model on the new situation that occurs. If the world changes rapidly, you have to rapidly adjust the model. And this is something we can learn from machine learners. And that's the end of my part. And for me, the challenging part is switching back to, this is okay, yeah.
Yeah, thank you, Pete.
Yep.
We received a comment for you. I can add it here. So this study on classification of saddest platform companies published somewhere is really interesting.
We're writing the paper at the moment, so we have the interesting thing of this study is the fact that you apply a machine learning model just to pre-select the companies based on the text of the website, and then send them a survey. And actually, the survey confirms the fact that the machine learning approach is working really well. And this is something I was very interested in as well. But we hope that the paper is finished before the summer. So it would be great to share it with you. And there's also a student involved, so perhaps it's possible to give you an idea of the works you've done by sharing the student paper. I'm not sure if that's allowed, but that's the only thing we have on paper at the moment. So thank you for your question.
Okay, and we have another one. Could you maybe expand on why retraining on the new data doesn't work in regards to concept drift?
Now, the fact is that retraining on new data works if you classify them again, because what was actually happening here is the fact that your model was trained on a situation in which websites use particular words, but those websites, over time, the text on those websites change. So what you have is that the world is quite dynamic. So what's happening is that the new data that you have doesn't reflect the situation that the situation on your classification. So what you need to do is adjust it to companies of which you know that are innovative and the words they use. So you need to constantly look at your model and rebuild it. It's quite challenging to do that on a very short period of time. It works really well. But if you would train a model on the data you have and use it, for instance, for data that's a year old, that's not a good thing. You should include new cases as well. The other solution that really works is dramatically increase the number of classified cases, and that's the solution I'm using at the moment. I'm using 20,000 classified websites to train a model. So because it makes it more representative of what's going on in the real world. I'm using my own explanation now to do that. Great questions. Thank you.
Thank you, Pete. So I think we can go on. Yeah. Okay, we can go on with the last part. So Marco, please.
Okay, I hope you all can hear me. If not, I will get a private chat, or we will just, because something went.
Yeah,
perfect. Okay. Yeah. So I like the subject about explainable AI, and I will explain why I like it. When I first heard it, I thought, well, that's a strange subject. And but when I started to read into it, I found out that it is actually something that this person who wrote this book, David Marr, actually proposed in '82, and he didn't propose it for machine learning, actually, and artificial intelligence, but he explained it to find out how humans function. And this is actually the first slide I will want you to show. So what he states is actually the best way to validate a model. Well, actually, he wasn't talking about validation and models, but the best way to do it is actually by understanding how the model is functioning. Understand how the model is functioning. And Marr described in his book, somewhere at the beginning of the book, so you don't have to read all the book for it, that when you want to understand an information processing device, the best thing you can do is look at it at three levels. It's at the level of the computational theory, it's at the level of the representation and algorithm, and the third one is the implementation. Now, Marr didn't finish the book himself because he died before he could publish his book. It was actually Tommaso Poggio who finished the book and published it. And Poggio came much later with the point that there is actually a fourth dimension where you should look at the data at, and that's actually the dimension of learning itself. And in our case, I can imagine that we would translate it like understanding the training set, understanding the annotated data that we are using for training the model. But let us go back to the 3 levels of Marr and what he actually meant. So the computational theory is actually about the environment where the model is actually working on. So you can imagine that when I'm training a certain model, that it is really good to understand how I got to that data set. And I would like to use as an example getting solar panels from aerial images. Suppose I'm going to detect solar panels and aerial images, then it is actually very good to know how the effect of the air between the plane and the roofs that you are actually looking at, how that air influences the image. We call that aerial perspective within physics. It is very interesting to see what the reflectance is of the solar panels and how it how they are actually related to the reflectance of the roofs. And you see actually that they adjusted the solar panels in such a way that you won't be able to see them very well. So it's really good to understand the physics behind the object that you are observing. When you are looking at symptoms on social media, a subject that I worked on quite recently, then you will see that it's quite interesting to see the reason why people are posting that they have a certain symptom, to understand if this symptom is real or not. So the computational theory behind it is quite good. And what you look at is the question, what is the goal? What is the goal of your information processing device? Why is it appropriate? Why is it appropriate to use the algorithm that you are using, to use the process that you are using? And what is the logic behind the strategy that you are using? So the representation and the algorithm is what a lot of IT people would call the design pattern. Which implementation are we using for a classifier? Which classifier are we actually using? What kind of parameters can we adjust? What is the input and the output of the classifier? Is there some other process around it? So we are actually refining how the design is of your information processing device. So it's actually how the process is formed. And finally, the implementation. Marr called it in his book the hardware implementation, because he was looking at the brain and he wanted to make a distinction between processes which run in the brain and processes which are simulated on computers. And the implementation is much about how is it implemented, which platform, which environment are you using to implement it, which language, what is the what are you using GPUs in case of neural networks or other things that take a lot of computation. So yeah, it's a question about how is it realized, the thing. And when I started to understand that this was actually what I was doing as a psychophysicist, I started to get enthusiastic, because I understand then what I'm doing. When you look at Explainable AI, there is actually a very good blog of Bahadur Khalegi. I hope I pronounced his name correctly. Probably not, but he has written a series of blogs on Medium. And if you look at this URL, you will find a lot of information about Explainable AI. He also has a lot of links to papers there, so you can actually go into that. And he actually proposes also 3 stages: a pre-modeling stage, explainable modeling stage, and a post-modeling stage. And what he actually says is that you should should use one of the 3. Whereas when you look at Marr and the school where I come from, then you would say try to use as much as possible for your explainability. So we start with the post-modeling explainability. It's about how can I figure out what the behavior is of my machine learning algorithm. So this is actually doing psychophysics on experimental neuroscience on a model. So backward propagation is about what neuroscientists would do when they refer to Hubel and Wiesel. We are going to put a probe into the skull of an animal, or we are going to use an fMRI scan and see what image do we see at the moment that we look in the brain about the receptive fields that are there at the moment that I present something. So that's one of the approaches. That's backward propagation. So you look at a certain node in your neural network and you propagate it back to the input. And at the moment that you arrive at the input, you can actually see what kind of images would result in an activation of that node. Another interesting part is the perturbation mechanism, which I wanted to mention, is actually doing psychophysics on the models. So you are going to look at the feature space, you pick a point in the feature space, and you are going to change one of the parameters, one of the features, and see how it changes the behavior of your model. The first one I called is an open box model. So you are actually opening the model and you're looking inside to see what is going on. The second one I talked about is a closed box. When you look at Bahadora, he actually says that the open box is better than the closed box. Me, as a psychophysicist, would say the closed box is better, but at the end, I think you should use whatever you can use and use it well. So maybe you should both, so to explain your model. Pre-modeling explainability is about understanding your data. So before you start creating a model, look at what data you have. And I mentioned it before in one of my parts I presented. It's really good to understand your data. It's really good to understand what is going on with your data. And it's very good to explore the data before you start to build models. It's good to understand how some parts of the data set are related, how some features are related. And one of the things what I like the most is the explainable feature engineering, where you start to put knowledge into your domain knowledge into your model. At the moment that you have an AI company, probably all the websites will have something about artificial intelligence on there. So it's good to have features in there to add features there which say something about artificial intelligence. So that's a pre-modeling. So I explained post-modeling and pre-modeling. Then we have the explainable modeling, and this is actually the part where a lot of people start to look at the moment that they start to investigate explainable AI. And the thing is that there are some modeling techniques, for instance, when you use decision trees, and partly also when you use logistic regression, which are explainable from themselves already. And when you use them, then you actually get a explainable model already. So it's actually a good starting point to have a method which is explainable. There is one caveat, and that is that most of the explainable models are simple models, and you cannot have a very complex structure put in there to make sure that and see a very good modeling functioning model at the end. So for that reason, people came up with the idea of hybrid models. But the thing is that I don't believe that much in hybrid models. But a hybrid model is that you use an unexplained or black box model at the beginning, and you add something explainable at the end. But still, the black box part is still some manipulation of your features, which could be interesting to see what is actually going on there. So that's another one. So then I come to the conclusion of the presentation. And actually, the explainable AI was already a little bit of a conclusion. But what I would like to do within this conclusion is actually go back to official statistics and go back to the dimensions of quality in official statistics. So when we look at it, when we take away all the quality dimensions which refer to time, because that's for now it's not a problem. Then we see that we have relevance, accuracy, accessibility, and clarity, and coherence, and comparability as subjects. relevance, we already saw that that part come back in explainable AI. Accuracy, we already saw that when we were talking about biases, for instance. Accessibility and clarity, we saw that coming back also in explainable AI. And coherence and comparability, we saw that coming back at the moment that Pete was actually talking about causality and correlation when he was talking about concept drift. So all these subjects came back here, and this is actually the reason why I started investigating the use of artificial intelligence and machine learning within official statistics, because we have very strict rules when it is about these subjects. So although machine learning is a very interesting area, and although there has been done a lot on machine learning in the past, we see that when we look at it from an official statistical point of view, we see that there are still subjects not really covered, and we are trying to investigate these topics as good as possible. That's actually the take-home message I have here. So we learned a lot from machine learners, but still there is a lot of things to do before we can say these methods are really part of the statistical toolboxes in official statistics. Thank you very much.
Okay, thank you. Thank you, Marco, and thank you, Pete. Okay, again. So for the moment, we'll see the final, I would say, common question from Monica, which is something that you already maybe addressed. So thank you both for your interesting talks. So a statistician, so on what concerns the statistics parts, on the basis of your experience, which part of statistical analysis methods would you recommend as most relevant for AI?
Yeah. It's hard to choose because all of them are really relevant. So I like the question of Monica because I can stress again that all of them, but maybe Pete and I can pick one or two. So I would say that the bias corrections are quite important for official statistics, and that the engineering of your feature space is very, very important for official statistics. So when I have to choose two of them, I would say those two. And I don't know if Pete has two others.
It's like choosing between your children. So
yeah, exactly.
They all have something very nice and something. But I think let's throw in the representatively part, because I think that's something where statisticians can really contribute. If you use AI on a particular data set, be aware of anything you do prior to developing a model. I think statisticians are very good in looking at the data and checking everything. I think that's an important part that we could add to all the AI research.
Yeah, and since Pete only named one, and it's really like choosing.
You're only allowed to name one.
No, you're allowed to name two. So I said one or two. So I would also say that the annotation part is really important. It's one of those subjects which are really making a difference in machine learning, and I think when you look at the way we look at questionnaires within statistical offices and how we design them, it's really a topic official statisticians could work on. So yeah.
Okay, so we receive another question. Then we are also running out of time. Any advice on planning sample size for ML training and test sets?
I can easily answer that, as large as possible. But I had a surprise in the first study we did on platform economy detection. I only had a very small set of positive cases. I only had 230 positive cases, but the findings that machine learning methods found on those kinds of examples those results were fairly consistent on a larger data set. But in principle, you want to have quite a large number of examples, because the more examples you have, the more you're able to extract the relevant features in your data set. The only downside is of a really large data set is that the models starts to increase as well. So
yeah,
1,000 or more would be great. Yeah.
Yeah, and for that reason, because of the fact that you cannot just add everything all the time, I'm also looking at a project within Statistics Netherlands where we are actually thinking about using everything we know about sampling theory, for applying that on creating our training and test set. So, look at stratification, look at the variance which comes out of the model, and use this information actually to determine the optimal sample size of your training and test set.
Okay, thank you. So, of course, you can add any reference, also the ones that you were mentioning before, maybe at the end of the slide, so that will be available for all the participants. So we are, I think, out of time. I don't see any other questions, so I think that we can conclude. So thank you, Peter, Marco, really for this very interesting presentation, and many thanks, of course, also to all our participants who joined us today from many different countries. You can already download the presentation from the EMOS 2020 events website. The recording of the webinar will be available on this YouTube channel. In the meantime, I kindly ask you to check the inbox of the email account you use for registering to the webinar, as you have already received the link to a short survey about today's webinar. We'd really appreciate your feedback to further improve our webinars. So while this was the last webinar of the spring session of the EMOS 2021 webinars, we will keep you updated on the program for our autumn session for the EMOS webinar. We really hope that you will join us again. So thank you for now, and have a nice evening.
Okay.
Bye-bye. Bye,
Bye-bye.
everyone.
Bye-bye.